back. So we have seen the operational amplifier definition relation when we consider it as an ideal operational amplifier. That definition relation was this. Now we are saying, we know that inside this operational amplifier there are many transistors and many other components in it, and another model of it that we use, it is called alternative model for OPAM, or sometimes it might called realistic model of an operational amplifier. That is the ideal one, and that's the definition relation. And the alternative model is this one, which has got two resistors in it and one dependent voltage source, of which voltage is this dependent voltage source voltage is Vp minus Vn times A. Now in this model we've got three parameters. One of them is Ri. Let me go in details. So Re is one parameter, R0 is the other parameter, A is, we already seen, an open loop gain it is called. So Ri is the input resistance, R0 or output resistance, or Ro is the output resistance. These are some of the practical operational amplifiers, each column here, for different manufacturers' operational amplifiers available, and you can buy it in the market. And these are these parameter values of these operational amplifiers. As we already see that the A open loop gain is in the range of 100,000, which is 200,000 and 100,000, 200,000, 1 million and 20,000. In here input resistance is 2 mega ohm. It's a big resistor value. If you look at this one, it is 1 tera ohm, means 10 to the power 9 is giga, 10 to the power 12 is the tera ohm. So it's very high value. Very high value resistor means the current passing through this resistor is going to be very low, isn't it? Because current of the resistor is V over Ri. If the Ri is very high, as DC in Y tera ohm, then this current is very small. This current, this small current, we represent in the ideal operation amplifier definition relation as 0. But we are not considering this in this model. It might be a current, but a small current, you can say. The output resistance, which is this resistance, is a small value in general. For this one, the quality is not so good, 75 ohms. But this one, it is just 1 ohm. So this is a very small resistor value. The output current is going to be, because of this input current is very low, we already said, so it is for these different operational amplifiers, the input currents are shown here. That is 10 to the power minus 12. How small it is, that you can imagine. So what we are seeing, what we are saying here, in this model, we are representing operational amplifier not by using a definition relation, but rather a model, a circuit model. In this circuit model, I have got three parameters. These are the range of these parameters. Then how I am going to apply this model instead of using the definition relation on operational amplifier is some of the examples that we've got here. Inverting amplifier and non-inverting amplifiers, the inverting amplifiers that we use in this application series, those two. And if I use not the ideal operation amplifier but this model, this circuit becomes this. So if you look at this circuit, go inside. So this is the operation amplifiers that we replace with this model. If you do the calculation, you end up with that result. So when you say that, okay, I can't do this, you don't say that, because this is a circuit, a resistive circuit, isn't it? We have analyzed all the resistive circuits, so you could do that. So you're going to find all the elements, you're not going to find all the elements current and voltages because I am dealing with only the output voltage here. So you can write the output voltage in terms of this independent voltage source voltage. That is it. So we have seen on the previous frame here that A value is very high value and the input resistance is very high value and the output resistance is very small value. So that means RE is equal to 0, RE goes to infinity, and A goes infinity. If you replace all this in this equation, you end up with that result. That result is the same as the one that you use the definition relation of ideal operational amplifier in here. So I am saying this here. We used its definition relation. We end up with the gain like this, and we did it by using this model here. It became the same thing. When you connect a RL load here, you're going to see that more or less the same. So there's no difference between this one and this one when you choose these values as it's shown here. What happens when the inputs are interchanged? That's the good question. So this whole result is going to be different. So you try and then find it out. So let's come to this one now. When the non-inverting case, if you don't use the definition relation of the operation amplifier by using this new model that we just introduced, then you end up with a solution like that. So this solution is V0 find out in terms of Vg. So once again, this is a resistive circuit, so you could do the analysis. In this analysis, you're going to calculate only that V0 value. You might say that this is Thevenin equivalent voltage as well. So if you replace these values with these values, the ideal values, you end up with that result, which is the same as the one that you found already. And then if you consider the whole chapter now, we introduce a new element, a bit different from the other elements that we have already seen. And we use this element definition relation as we consider this element as an ideal element and gave a very simple definition relation of mathematical relation, which helps us to do the fast and simple analysis. And then we said there are some practical circuits which includes the operational amplifiers in it. These practical circuits has been analyzed here. And then we said if you don't use the definition relation and consider the operational amplifier non-ideal, then we introduce a new model. For this model, we have found out the outputs and compare it with the ideal case and the alternative model case differences. So that is the end of chapter 6.